Today we're going to talk about chemical equilibrium, which we started a little bit in class today, and we'll talk about the equilibrium constant and what that constant means for a particular reaction. So far this year we've only talked about forward reactions. So a forward reaction is when reactants are converted to products. So everything on the left is converted to something on the right. And that has worked really well for us so far, but it turns out that sometimes reactions can also go backwards. So the reverse reaction is when products are converted back to reactants, and this is what we call a reversible reaction. It's a reaction that can or does go both forward and reverse. Okay, and so what this looks like in terms of how the rate is happening and also the concentrations is shown here in these figures. So in terms of rate, we start with only the rate of the forward reaction. So it starts very high. That's because we only have reactants when we start most of the time. And so as those reactants are used up, the rate goes down. It goes down because as we use them up, their concentration goes down, and so then the rate slows. Okay? Whereas the reverse reaction, we start with no reaction because we don't have any products to convert back to reactants. And so as they are formed, then that rate also continues to go up, and as the concentration of products goes up, then that reverse reaction can happen. At some point, we reach a point where the forward rate is equal to the reverse rate, which is right here, and at that point is where we reach equilibrium. Okay, and I'll talk a little bit more about what equilibrium means, but it basically means that if the rate of the forward reaction is the same as the reverse reaction, then it looks like nothing is changing, even though things are reacting both ways continually. So how does this look in terms of concentration? So we start with all reactants up here and no products, right? And then as our reaction progresses, the amount of reactants will go down and the amount of products will go up. And at some point, if we're making products at the same rate as we're converting them back to reactants, we'll reach equilibrium, and these concentrations won't change. So that's what equilibrium looks like. It looks as though nothing is changing, but sometimes it's called dynamic equilibrium because something is actually happening, but the net result that we see is that nothing changes. Okay, so chemical equilibrium, like I just said, is when no further change takes place in the concentrations of the reactants and products, even though the two reactions continue at equal but opposite rates. Now here we have a reversible reaction. We have H2 plus I2 goes to 2HI, and this is the reaction we did in our activity in class earlier this week. Okay, and so when we start off, usually we start off with just reactants. So we have our I2 molecules shown in dark here. There's 4 of them, and there's 4 H2 molecules, which are the little double white atoms right there. Okay, so our concentration of reactants is going to be 4 H2s and 4 I2s, which they're calling a total of 8. All right, this is when our reaction starts. And we don't have any products at this point because nothing has happened. At this point, the concentration of our reactants is high, so our forward rate is also going to be fast. Okay, so if we let that go for an hour, then we look and we have 3 H2s and 3 I2s in this circle here. And we also now have 2 HIs, so one here and one there. Okay, so our forward rate is still going to be pretty fast, but we've now got a little bit of product, so our reverse rate is going to appear, and those products are going to be able to be converted back to reactants. Okay, and then as we continue on, you can see that the forward rate continues to get a little bit smaller, and the reverse rate keeps getting bigger until we get to the point here at the end, or sorry, here, number part D, where we have 2 reactants left and 6 products. So we have 6 HIs, and then we have 1 each of the H2 and the I2. Okay, and even if we let that sit for a while longer, so this is to 24 hours, those concentrations don't change. So these numbers are the same, and these two numbers are the same, and you can see that the rates haven't changed either. And that's the way equilibrium works. It will change until it gets to the point where the forward and reverse rates are equal but in opposite directions, and then the concentrations of our products and reactants will no longer change. All right, so we represent this mathematically with a concept called the equilibrium constant. So if we have this generic reaction here, AA plus BB, and we use these double arrows like this to represent a reaction that is reversible, then that becomes CC plus DD, where the little letters represent our coefficients and the big letters represent our molecular symbols. So we can write our equilibrium constant expression as the concentration of products over the concentration of reactants. Okay, so that's going to be equal to the concentration of C, and then there's a little c here, that's the exponent, and that's our coefficient, times the concentration of D with the little d exponent, divided by the concentration of A to the A times B to the B. Okay, so this looks a little bit weird, but we're going to do a lot of practice with it in class, and you will get more comfortable with it. Now, an equilibrium constant expression is just that. It's the concentration of the products raised to their coefficient as a power divided by the concentration of the reactants. So now, let's talk about homogeneous equilibrium. So homogeneous equilibrium is when all of your reactants and products are in the same state. So for example, they could all be solutions or they could all be gases. Heterogeneous equilibrium also can occur, but that's when we have the products and reactants in at least two different states. And it's important to note that our equilibrium constant expression will exclude solids and liquids. So we only are going to include concentrations in molar, and for gases, we could either have the concentration in terms of molarity, or we could also have it as a pressure. Now let's do two quick, easy examples to just show you how this works. So Kc for this first reaction here is going to be equal to the concentration of the product, so that'll be the concentration of Hi squared, because it has a 2 coefficient here, divided by the concentration of H2 times the concentration of I2. That's your whole equilibrium expression. And if we knew the concentrations at equilibrium, which we could measure experimentally, then you could plug those in and get an actual value. Okay, and then the second example I have here is calcium carbonate going to calcium oxide plus carbon dioxide. And in this case, we have a heterogeneous equilibrium, okay, because we have both solids in this case and gas here. Okay, so the Kc for this one would be equal to the concentration of CO2, which is one of our products, and then we won't put the concentration of calcium oxide or calcium carbonate into the expression because they're both solids. So we always exclude solids from our equilibrium expression. So now let's, now that we have these expressions, this is the expression we just did in the first example on the previous slide. So let's see how these work in terms of actually doing the calculations. So for the first one, we're going to do 1.04, which is the concentration of Hi, squared, divided by the concentration of H2, which is 0.10, times the concentration of I2, which is 0.20. And if we multiply all that out, we get 54. Okay, so for the next one, we'll have 1.47 squared divided by 0.2 times 0.2, which is going to give us 54. And for the third one, we have 1.66 squared divided by 0.3 times 0.17, which again gives us 54. So the equilibrium constant, as you would expect from the name, is constant for a given reaction at a particular temperature. So if we were to change the temperature, K would also change. But at a particular temperature, it doesn't matter what your starting concentrations are, you will eventually get to concentrations that when plugged into your equilibrium expression give you the same value for K. Now, why do we care about the equilibrium constant? Well, the equilibrium constant tells us a lot about the nature of the reaction. So if we have a Kc, that means that we can perform, that both the reverse and the forward reactions occur, but we don't know to what extent they are favored. And so the value of Kc can give you an idea of how many reactants and products will be present at equilibrium. So if Kc is approximately 1, then that would mean we have pretty close to the same amount of reactants and products. Okay, so that would be this example here in the middle. If we have a large Kc, which is over on this side of the continuum, then that tells us that we have a lot more products than reactants because products are what are on the top. So if we have a big numerator and a small denominator, that will give us a large Kc. All right, and then on this side, if we have a small Kc, that means that the top number, our numerator, will be small, and the bottom number, our denominator, will be larger, and so that means we have mostly reactants in this case. So if you want to fill in the blank here based on that information, you know that a large Kc, which we're going to define as bigger than 10, means that the forward reaction produced a large amount of products at equilibrium. And a small Kc, which will be less than 0.1, means that at equilibrium there is a large concentration of reactants at equilibrium. So that wraps up our discussion of equilibrium constants, and we'll next time we'll talk a little bit more about how we can modify the equilibrium or shift it to make more products or more reactants depending on our purposes.